particulate nature of matter. We defined matter as anything that has mass and occupies space. Matter can exist either as solid, liquid, or a gas, and these are called the three states of matter. For a very long time, people thought that matter was something continuous, meaning that it is one smooth and broken thing. But today we know that matter is made up of tiny distinct particles called atoms, from the Greek word atoma, meaning indivisible. So you cannot break an atom further. This is water. Water is a liquid. A liquid is made up of particles called molecules that move in random directions. But the problem is that these molecules are too tiny to be seen even with a powerful microscope. But the proof that water is actually made up of distinct molecules is very simple. I'm going to add a drop of green food coloring and watch what happens. I will now put you into time lapse so that it doesn't become boring. And there we are. The dye has spread all through the water. I know you are wondering, what on earth does that prove? It is very simple. What is happening is that the molecules of the dye have occupied the spaces in between the separate water molecules. Look, if water was continuous and no spaces in between the molecules, then the dye would have no space to occupy and will not mix. Think about it this way. If you want to mix with a crowd of people, really there has to be a space in between the people in the crowd for you to fit in. And that is exactly what is happening to the molecules of the dye. I hope I convinced you. You see, sometimes science can be found in the simplest of things. The other idea of the particulate nature of matter is that particles are in a continuous random motion. They are not static. As they move, they collide with each other. It is the collision of the molecules of the dye and those of water that allows the dye molecules to spread on and occupy the spaces ahead. This random movement of molecules was first observed nearly 200 years ago using pollen grains produced by flowers. A botanist, Robert Brown, was carrying out his studies on pollen grains. He crushed the pollen grains and suspended them on water. But Brown was very annoyed because the pollen grains continuously jetted around, giving him a very hard time. Today we can see the same effect by looking at tiny carbon particles instead. A drop of carbon powder is suspended in oil, placed on a slide and viewed under a microscope. The carbon is seen as dancing around. Brown did not understand why this occurs, and it was Albert Einstein who explained that the particles of any matter are ever in a continuous state of motion and never static. It is during their movement that they collide with each other and with other particles. This is called Brownian motion. Normally, in order for this dye to mix completely, I would have to stir. But you see, it's completely unnecessary. Brownian motion causes the molecules to collide and move in all directions. Brownian motion is also seen in gases like air. We can demonstrate this by looking at the behavior of smoke particles under a microscope using a smoke cell. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light enables it to be seen under a light microscope. It appears like tiny jittering points of light. When a straw burns, the smoke produced is mainly made up of pieces of carbon which are not fully combusted. Under a microscope, they cut the light into glittering particles. But why do they dance randomly around? The movement of smoke is caused by collision with the invisible air particles. As the air particles move about, they knock the smoke particles in all directions. Particles in a gas move randomly and quickly. All these experiments sum up to what we call the kinetic theory of matter. The kinetic theory of matter states that matter is made up of distinct tiny particles which are in a continuous random motion. The motion of these particles varies depending on the state of matter, whether it is a solid, liquid, or gas. If you consider water, in the iceberg, water is solid, in the sea, it's liquid, and in the surrounding air, it's a gas. Solid, liquid, and gas are the three states of matter. Solids have definite shapes and volumes. In solids, the particles are in a fixed framework. They are held close together by strong cohesive forces, and they vibrate within these fixed positions. When heat is supplied, the cohesive forces begin to weaken and the kinetic energy of particles increases, causing them to vibrate more vigorously. At a particular temperature which is specific for a particular solid, the particles have enough kinetic energy and overcome the forces of attraction, setting them free, and the solid melts into a liquid. This is the melting point. Liquids have definite volume but no definite shape. They assume the shape of the container in which they are put. Particles in a liquid are slightly free but still experience some attraction forces between them, so they are not entirely free to move around, and this is why liquids still have definite volumes. The slight mobility or freedom makes them have no definite shape. An increase in temperature increases the kinetic energy of particles and weakens the forces of attraction. At a specific temperature, which again is specific for a particular liquid, the kinetic energy of the particles is enough and the particles overcome the forces of attraction, setting themselves free, and the liquid vaporizes into a gas. This is boiling point, and the process is called vaporization or evaporation. Gases have neither definite shape nor volume. They fill any container in which they are put. The particles in a gas are far apart. They move quickly, randomly, and in all directions. Now the reverse processes take place upon cooling. When temperature is lowered, gas molecules lose their kinetic energy. Forces of attraction build up until the gas condenses into a liquid. Further cooling results into the liquids freezing back to solid. Notice that melting and freezing occur at the same temperature. Evaporation and condensation occur at the same temperature. Certain substances transit directly from solids to gases, bypassing the liquid phase. This is called sublimation and is seen in iodine crystals. The next aspect is diffusion. If someone lit a cigarette at one corner of a room, the not-so-good smell is eventually felt all over the room. And this suggests that the smoke particles have moved from one point to another. Understand that the smoke is highly concentrated near the cigarette compared to other parts of the room where initially there is no smoke at all. The smoke therefore spreads from a region of high concentration to a region of low concentration. This process is called diffusion, and it is defined as the process by which particles spread from a region of high concentration to a region of low concentration. Diffusion occurs in both liquids and gases. If you put a few crystals of potassium permanganate in a jar of water, the purple color spreads throughout the water until we have a uniformly colored solution. The particles spread from where they are highly concentrated to where they are in low concentration. Diffusion in gases. Now, diffusion in gases is faster because the particles move faster and randomly compared to liquids. We can illustrate diffusion on a small scale in the lab using bromine, an orange-colored gas. We invert an empty jar at the top of the jar containing bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the two gases mix. After about 30 minutes, both gas jars have the same color. But why does it take that long? It takes time because bromine molecules are colliding with the air molecules and against each other, slowing them down. As you can imagine, bromine would diffuse faster if there was no air to bump onto. Look, all the air have been removed from this apparatus apart from the flask containing bromine, which has a tap. Open the tap and see what happens. It spreads immediately. Watch that again. In a vacuum, there is no air molecules to collide with, so the bromine diffuses much faster. You see now, diffusion is slow when the apparatus are full of air. Good. Let's look at the rate of diffusion. What factors affect the rate of diffusion? Observe that these two containers have equal volumes of water, but the beaker on the right has hot water. I want to add drops of dye simultaneously and see which one diffuses faster. Alright? Here I go. Whoa, I didn't think that was simultaneous, but it's going to work anyway. You see, in no time at all, the dye in the hot water has spread almost completely while the other is still struggling, even though the drop of dye appeared to have been a few seconds late. So diffusion is faster at higher temperature, of course because the particles have higher kinetic energy and therefore move faster. Let's see the diffusion rate between two gases. Nitrogen dioxide on the left is similar in color to bromine gas, but the bromine molecules are much heavier. The lighter nitrogen 4 oxide diffuses rapidly. We can also compare the rates of diffusion of ammonia gas and hydrogen chloride gas. Both are colorless, but when they meet, a white cloud of ammonium chloride forms. A piece of cotton wool soaked in concentrated ammonia solution provides ammonia gas. Concentrated hydrochloric acid provides hydrogen chloride gas. Place the two cotton wools at the opposite ends of a tube and the gases spread out. You can compare the speed of diffusion by looking out for the cloud of ammonium chloride. After less than a minute, a white ring begins to form, marking where the gases meet. The cloud is closer to hydrogen chloride, meaning ammonia diffused faster. You can also monitor the progress of the gases using a wet indicator or litmus paper along the tube. Hydrogen chloride makes it red, ammonia turns it blue. Ammonia travels faster because it is lighter than hydrogen chloride gas. So the rate of diffusion is also influenced by the weight of the diffusing gases.
This is my own and my soul. This is my own. I have a goal. I believe I will succeed in my goal. This is my own.
Islington College.